Hey guys, today we are going to find determinants and inverse of matrices. So we'll start with determinants. First of all, something we need to know about a determinant is it must come from a square matrix. Okay, well, a square matrix, what that means is a matrix that's maybe 2 by 2, 3 by 3, whatever the number of rows is, it's the same number of columns. Okay, so that is a square matrix. Okay, the matrix is used as the denominator in the inverse matrix. So what we do here, learning to find a determinant, will help us find the inverse of a matrix. So given matrix A, there's two ways we can be asked for the determinant. One, it can look like this. Determinant and then the matrix. So this is asking us to find the determinant. Another way that you can be asked for a determinant to look like this. Notice the difference, there's these brackets here. We don't have that little horizontal part. So either saying DET for determinant and then the matrix, or just giving these vertical brackets without the horizontal parts also says find the determinant of that matrix. Okay, second order determinant. So finding the determinant of a 2 by 2 matrix. Okay, so when we find the determinant of a 2 by 2 matrix, we do the main diagonal product, A1 times B2, minus the secondary diagonal product. Okay? That first diagonal product is positive, second diagonal product is negative. So you've got positive, then negative. So we'll find the determinant of this matrix. We've got 7 times 5, and that's the positive one. That's the main diagonal. Then the secondary diagonal will be negative 3 times 4. So that's 35 minus 12, which is 23. Okay? And here's the other notation. So we have the DET notation, and here we've just got the vertical pieces without the horizontal. It's just asking for a determinant again. The main diagonal, 4 times 5, that's positive. Secondary diagonal is negative. Negative 2 times 3. So that's 20 minus negative 6. So that determinant is 26. Okay, we'll do a third order, and this is the highest one that we'll do. This one's a little bit more complicated. So we still follow that pattern of positive, negative, but there's a third column now. Positive, negative, positive. Okay? So what we do first is this first element in the top row multiplied by the determinant from this matrix. So we start in the first row, then we find the determinant of the matrix in the next 2 rows. Okay? And then we move over to the next column, and we use this, and we multiply that by the matrix from these 2 outer columns. And then we move over to this third column, and we multiply that by the matrix made from these other 2 columns. So whatever column you're in the top row, you're using the other 2 columns in the bottom 2 rows. Okay, so here we go. 7, and this one is positive, and negative, then positive. So we've got positive 7 times the matrix from these 2 rows down here. So bottom rows and bottom columns, or bottom rows in the right 2 columns. So we've got the main diagonal, negative 1 times negative 3. minus 6 times 2. Okay, so then we move over to the next. I'm just going to change colors here. Get that. Okay, so I'm going to use that number. So it's minus, because that's a negative one, negative 5 times, and then I use a determinant from these outer two rows. 3 times negative 3 minus negative 2 times 2. Okay, and then I'm going to move over to here. Forgot to close that bracket. Okay, so then we're in a positive one, so plus 3 times the determinant from this matrix. So I've got main diagonal of 3 times 6 minus the secondary diagonal, negative 2 times negative 1. A lot of times people set these up and still make mistakes in their calculations, so we need to be careful as we calculate this. Okay, so we have 7 times 3 minus 12 minus negative 5 times negative 9 minus negative 4, so that's plus 4, plus 3 times 18 minus, and then negative 2 times negative 1 is 2. Okay, so that's 7 times negative 9, so we get negative 63 minus, we've got negative 5 times, and then negative 9 plus 4 is negative 5. So negative 5 times negative 5 is 25. And plus 3 times 16, which is 48. So negative 63 minus 25 plus 48, and that is negative 40. So the determinant of that matrix is negative 40. Okay, so we'll try another one. So we start with negative 8, and we use the matrix down here. So we've got negative 8 times, and this time we'll just skip ahead a step. So we've got negative 30. So instead of writing what we're multiplying, we're just going to multiply it. And 1 times negative 1, so it's minus negative 1. Okay, so that was the positive, now negative. Then positive. So 2, and then we're going to use the 2 outer columns. So 2 times 4 times 5 is 20, minus negative 3 times negative 1 is 3. Okay, then we're in a positive column. 7 times, and then we use these 2 rows away from that 7. 4 times 1 minus negative 3 times negative 6, which is 18. Okay, if we put all that together, so we've got negative 8 times negative 29 minus 2 times 17 plus 7 times negative 14, that will give us 100. Okay, inverse. The inverse of a matrix. Okay, so given a matrix, and knowing that its determinant does not equal 0, Then the inverse, which is notated like this, so this A -1 means inverse, is 1 over the determinant times, so this is going to be scalar multiplication, and it's our original matrix except these got switched on the main diagonal, and on the secondary diagonal, their signs became opposite. Okay, so the first thing we have to do in order to find an inverse is first find the determinant. So the determinant of a second order, we've got -3 times 7 minus -8 times 2. Main diagonal minus secondary diagonal. Okay, so that's -21 minus -16, and that is -5. So the determinant is -5. Okay, so now that I have found the determinant, I can find the inverse. So the reciprocal of the determinant is 1 over -5, and I multiply that by our matrix, except I switch the main diagonal, so 7 and -3 switch places. And the secondary diagonal gets opposite signs, 8 and -2. Okay, and now I do scalar multiplication. -1/5 times 7 is -7/5. -1/5 times -2 is positive 2/5. -1/5 times 8 is -8/5. And -1/5 times 3 times -3 is positive 3/5. So this is the inverse matrix. Okay, so let's try another one. First, in order to find the inverse, we must find the determinant. So the determinant is found by doing the product of the main diagonal minus the product of the secondary diagonal. Okay, so that's 30 minus 12. So the determinant is 18. Okay, so now I use the reciprocal of the determinant, 1 over 18, and multiply that as a scale factor by this matrix with the main diagonal switched, so the 5 and 6 switch places, and opposite signs on the secondary diagonal, -3 and -4. So I've got 1/18 times 6, so that's 6/18, and that simplifies to 1/3. Okay, -4/18, so that's going to be negative, and 4/18 is 2/9. -3/18, and 3/18 is 1/6. And 5/18, and that does not simplify. So that is the inverse of the matrix. All right, an identity matrix is a square matrix with 1 along the main diagonal, 0s elsewhere. So an identity matrix, say in a 3x3, would look like this. Main diagonal is 1, everything else is 0s. You can have that in any size square matrix. Okay, so when you multiply an inverse, or a matrix by its own inverse, that actually gives you an identity matrix. So the matrices here, 5, 4, 3, 6, that's the same one from above, right here. We're multiplying it by its inverse, 1/3, -2/9, -1/6, and 5/18. So if I went through the multiplication on this, I would end up finding that my product is this, 1, 0, 0, 1. I'm multiplying by an inverse. Just like if I multiplied a number like 5 by its reciprocal, I would get 1. Okay, so what this is, when you multiply a matrix by its inverse, it's essentially multiplying a number by its reciprocal. When you multiply a number by its reciprocal, you get 1. When you multiply a matrix by its inverse, you get an identity matrix. So essentially, the identity matrix is to matrices what 1 is to other numbers in multiplication. Okay? It is the multiplicative inverse that gives you the identity matrix. 1 is the multiplicative inverse. 5 times its reciprocal is 1. Okay? If I was to multiply this matrix by an identity matrix, 5 times 1 is 5, 4 times 0 is 0, 5 plus 0. Okay, next column, 5 times 0 is 0, 4 times 1 is 4, 0 plus 4. Next row, 3 times 1 plus 6 times 0 is 3. And 3 times 0 plus 6 times 1 is 6. So multiplying a matrix by an identity matrix is the same as multiplying a number by 1. 5 times 1 is 5. Okay, so when you multiply any number by 1, you get that same number. When you multiply a matrix by an identity matrix, it's essentially multiplying by 1. You get the same matrix.